Hello, everyone. Okay, we have the slides. We would like to talk now about Grackle, which is GraphQL server. But let's start with a very short introduction. So my name is Rafał Piotrowski. I am a Scala developer working for Iterators, which is a software house company located in Poland. You can find me on Twitter and on GitHub. And I have a great pleasure to co-present this talk with Sabin from Underscore, who is one of the authors of Grackle, but not only. You may know him as author of other projects, so for example, Shapeless Library. You can also find him on Twitter and GitHub. So we are now both working for ITV, where Grackle is used in several places. So you can see here itv.com service main page. Miles, can you say something more how Grackle is used here?
Yes. So Grackle is used throughout the ITV hub to provide all of the content level metadata associated with programs. So for example, everything that you can see on the screen here, which relates to series numbers, episode numbers, synopses, titles, the selection of content in particular Rails, that's all provided via a service which is implemented in terms of Grackle. And this is another part of the ITV site. It's the news site. And in this instance, again, all of the article-related metadata, so titles, synopses, like not the actual article bodies, but everything else related to that is again provided via a service which is implemented in terms of Grackle.
Yes, on backend, we also have one service that is using Grackle. So it's kind of aggregation service which aggregates data from multiple sources. It stores that data into SQL database and then expose that as GraphQL API using Grackle. We have now a few services that are already clients of this API, and we plan to have more, and it's working very nice there. And the last one, but not least, is something very interesting. Can you say something more about that, Miles?
I can. People may recognize the telescopes and the lasers firing into space from presentations that Rob Norris, aka T-Polecat, has given on a variety of occasions. So the initial work and current work on Grackle was sponsored by Aura Gemini, and their current application for Grackle is as the underpinning of the next generation observatory control systems, all the user interface components relating to that.
Okay. So we have already said that Grackle is GraphQL server, but we didn't said anything what GraphQL is. I suppose that most of you were already using some kind of GraphQL API or at least know what it is. But let's have now a very quick overview. So GraphQL was created by Facebook. It was made open source about 2015. It's an open standard. It's one of the ways how currently APIs are implemented and exposed. It's a structured query and manipulation language, quite flexible and powerful alternative to REST. And when comparing it to REST, GraphQL have schema. It has also types. And GraphQL client needs to choose what it wants from the server. It's also possible to define in schema how data can be modified. Also, it's possible to be notified about changes, which can be anything like events, data notification changes, or something like that. And we call that subscriptions in GraphQL. And now I will try to share my screen and show you, some demo. So here you can see a GraphQL playground, which is a web client to GraphQL API. This API is served currently by Demo app, which is a module in Grackle. It runs in the background. And the API is inspired by Star Wars movies. So we have here character, human, and droid. Character is an interface. Human and droids are types that implement that interface. We have also an enum, which corresponds to episodes of the oldest trilogy of Star Wars movies. And we have 4 root level queries. So we can request a hero for a given episode, and also character, human, or droid for a given ID. So let's try it, and let's request a hero for Empire Strikes Back episode. And we will get ID and name. Yeah, so we can see results here. It's Luke Skywalker. Let's request Luke by its ID. And now let's have a name. Let's have appear in, and also a list of friends. Yeah, you can see that we can invoke multiple queries in one request. Also, you can see that the structure of the query follows the structure of the schema. As you can see, we have autocomplete feature in this editor, which is possible thanks to the schema. And also the structure of the result follows the structure of the query. We have as well here a cycle. So the friends is a collection of characters, and it's in a character type. So it's possible to construct a query that has any number of levels we want, and it will work. Yeah, it works. Maybe not very particular, useful, but still possible. Okay, let's now get back to our slides. Oh, there it is. Great. So Grackle is a GraphQL server. It's powered by Cats, Cats Effect, and Circe. Currently, it supports in-memory and database-based model, which means that we can serve data from in-memory and from SQL database. And when it comes to the second option, we have ready-to-use integration with Skunk and Doobie. And for that, we don't need to define SQL queries. It's done by Grackle, and well, you will see that later. Grackle supports or GraphQL operations that are defined in the schema. So queries, mutation, and subscriptions. Mutations are available for all mappings. Subscriptions are currently available for in-memory mapping and for skunk mapping. There's also possibility to compose multiple schemas, mappings, and models, which means that we can serve in-memory data together with SQL database data in one GraphQL API. And the project is sponsored by ITV and Aura Gemini.
So that's the overview. How does it look underneath? Grackle is structured as a compiler, actually several compilers and an interpreter. So GraphQL queries, like the ones that Rafał showed you, are first compiled into an internal query algebra. The query algebra represents a core stable set of primitive operations which can be executed relative to some abstractly specified model data and interpreted in such a way that we can produce the structure of the JSON result we're looking for. Importantly, these query algebra terms that queries are compiled into, they are Scala values. They can be inspected, they can be manipulated, they can be transformed in various ways, and this is going to turn out to be extremely important. GraphQL queries are linked to the backing data via several related mechanisms. So initially, we're compiling the query to the GraphQL query to a query algebra term. There's an elaboration phase which exploits the value nature of query algebra terms to allow us to inspect and modify the term to layer application-specific semantics onto the queries. So in the examples that Rafał showed you earlier, he showed instances of fields which have arguments. So these are things which look like, a little bit like method calls in Scala, for example. The GraphQL specification doesn't give any specific meaning to what arguments to a field might be. There's really only syntax specified. So to be able to actually provide an application with a particular meaning, where we can say that providing an ID to an argument is performing a selection or a filter or a query of some sort against the data model, we need to provide application-specific semantics. So this is done in an elaboration phase. We also have a mapping layer which connects the GraphQL schema with whatever data source we're working with. The data source that was in play with the demo that Rafał just gave you is it's an in-memory data model. The values are Scala values, and the mechanism is making use of a generic shapeless-based model for interpreting the values. And in the end, we have a mechanism for, given the query, given the model, we're able to specify the output result by interpreting the query algebra term with respect to a cursor which is able to index into the model data, whatever form it takes. So as we're going to see a little bit later, we can also further compile and process the query algebra term that we've generated in a backend specific way if that's necessary to materialize data. And for example, we are able to compile the query algebra term into efficient SQL, which we're able to use in the database back cases. Okay, so this is these fragments of the GraphQL schema correspond to the demo that Rafał just gave you. So what we're looking at here is the GraphQL schema definition for the top level character field. As we can see, it's provided with an ID argument, and it will return a single character. All that we need to see here is this one top level method and the name field of character. This is the query we're going to walk through. We're just asking for character with ID 1000 and their name. So this GraphQL query is translated into this term in the query algebra. As you can see, it's a fairly direct translation. We've done some initial typing of the argument list, so we can see that that the ID is an integer which we're going to be using to select an item from the underlying data model form. And you can see that we have something here in the query algebra which reflects the nested structure of the GraphQL query. This is a snapshot of the sort of a minimized version of the query algebra. It's comparatively small. So unlike the grammar of GraphQL itself, which is quite large and complex, the query algebra is small and compact. It's the kind of thing in which you could imagine being straightforwardly interpreted against. You can consider a query algebra term as being a program which can be interpreted to produce some kind of result. That is what we do when we construct results. The range of terms in the query algebra is quite small. It's sufficient to interpret the generality of GraphQL syntax, and it's also sufficient for us to be able to add a lot of application-specific semantics. For example, you can see that we have a few terms here which will obviously be familiar if you work with databases or if you work with collection data types and things of that sort, so filter, order by offset limit, and so forth. So this is what happens after the first stage of elaboration of our query term corresponding to the GraphQL query. There's no defined semantics for field arguments, so we have eliminated those. You can see that the list of bindings has gone now, but the child part of the query has been elaborated to include a filter expression, and that will filter on a field of the underlying data type, the ID field being equal to a particular constant, and then the result of that filter is asserted to be unique, at most one element via the unique element of the algebra. So that's the query as elaborated into a sort of an executable query term. We need to have some additional information which relates the GraphQL schema to the underlying data. And in Grackle, this is done by way of mappings. Mappings specify GraphQL query types and their fields, and they tell Grackle how to interpret fields relative to the model. In this particular instance, it's a very, very simple mapping. We have a single top level field characters, which is mapped onto a character's value, which is essentially a Scala collection of algebraic data types, so nested case classes. The mapping being used here is the generic mapping. This is a generic field. Generic here is in the sense of data type generic programming. So This is backed by Shapeless 2 on Scala 2, by Shapeless 3 on Scala 3, and allows for a sort of path-based traversal of arbitrary Scala Scala values in the way that you would expect to be able to traverse the structure, to be able to pull values out. This is going to make use of a fairly direct correspondence between the Scala data type and the GraphQL schema. And this gives us our result.
Yeah, so we have also a second API, which we would like to show you. Yes, so we are back to GraphQL Playground. And this API is a little bit bigger. It's inspired by a list of countries and cities in the world. So we have a country type with several attributes and collection of cities and a collection of languages. Language type has collection of countries, while city has a country to which it belongs. So you can see we have a couple of relations here. We have also several queries that we can use here. We can request cities by pattern or by ID, countries by code, by population or by population, and independence year, as well as we can also search for some non-dependent areas. And some of the queries have some paging, filtering, limiting capabilities, as you can see. So let's try it. And first, I will try to find the city that I am currently located in. So we will use this query with patterns. And let's have a name and country. And here it is. It's Wrocław in Poland, so that's correct. Let's try to have now cities of, or maybe let's have, let's use the country query with out, and we will ask for a number of cities. And with that, we will get a list of cities from the United Kingdom. We can also use some advanced queries here as well. We can search for countries that have at least 5 million people and which are independent since, for example, 1950. And we will get a name, region, and population. And here it is. All of this goes from Postgres database that is running under the hood. So the queries are translated into SQL queries. So yeah, let's get back to presentation right now. And Miles, can you explain us how does it work in Grackle?
Sure. So like we did for the in-memory based demo, I'm just pulling out some fragments of the GraphQL schema which we can walk through. So here we're just going to look at the country top level field and a subset of the fields that we have in the country type and the city type. So here's the query we're going to look at. We're just going to do the one that Rafał did just now. We're going to query for the UK. We're going to show its name, for each of the cities, their names. So in a similar kind of way to the way we saw with the in-memory example, we're going to have to elaborate that query in a way which eliminates the sort of undetermined query arguments, field arguments, and turn that into something which actually captures the semantics of what we're trying to do. So it's very similar to the last example in that we're doing a filter of countries based on the value of one of their attributes. So we can see that we're looking for countries whose country code is equal to the constant GBR. And again, we're going to be looking for a unique one of these. So we nest this in the unique query algebra term, which asserts that that's the case. In this case, we have a slightly more complex query for values underneath that top level field. So we're looking for both the name field at the country level, but then we're also selecting cities, which are themselves structured values, and beneath those, their names. Now, there is more detail we need here in terms of how we actually connect the GraphQL query with the data source. We have a data source, it's a SQL database. We have a database schema, which looks like this. This is just a vanilla SQL database schema written as you would write it by hand. There's no constraints on it determined by the framework. Any database will be can work with this model. As far as Grackle is concerned, we need to have some way of specifying tables and fields if we're going to actually line the data up with the GraphQL schema and with the fields required for the query. And this is an example we're using Doobie. So we use infrastructure in Grackle to specify table names and column names and the corresponding Doobie metas, the codecs for reading values from the data store. Now, in this instance, the mapping is more interesting than the last case. As previously, the mappings are specified at the level of the GraphQL types. So you can see here we have two mappings. We have a mapping for country type. This is the type as specified in the GraphQL schema, and also for city type. And for each of these, we have field mappings, and these are field mappings again at the GraphQL level. So this is a mapping for the GraphQL code, name, and cities fields in the country type. And these are mapped to the SQL schema, database schema level, country code, country name, and fields. The cities GraphQL field corresponds to nested subobjects. So in this instance, we're going to be specifying that in terms of a join on the underlying database. We need to have some way of linking these types together, but we can do this in a relatively simple, direct way, just by specifying what columns we actually need to perform the join on, and whether we need a join or not is obviously going to be dependent on whether or not the GraphQL query in question actually requires a traversal through that link or not. There are a few additional details here which are important to the execution of the queries. For database-backed models, we do need to know that various fields correspond to database keys, and we have a mechanism for specifying that. You can see in a couple of the code field of country type and the ID field of city type are specified as being keys. And there are also going to be situations where there are things in the database which are relevant and which we need to work with, but which don't correspond to things which are in the GraphQL schema, and these are flagged up as hidden things. So we can decouple the GraphQL schema from the database schema to a significant extent. So, given all of those, the query term can be compiled into this SQL. This is pretty much exactly the SQL that you would write by hand. You might wonder what kind of SQL you would get for more complex queries, perhaps queries which are sort of nested or recursive or something like that. A great deal of engineering effort has been put into the SQL compiler over the last couple of years, and it is really very comprehensive. It can cope with some really very complex GraphQL schemas and corresponding database schemas. And this is the result we get. The result of the execution of the SQL query is essentially it forms the result data, which is then traversed by interpreting the GraphQL. By interpreting the query algebra term. So we have a cursor again indexing into the result set from the SQL query, and the effect of interpreting the query algebra term relative to that cursor is what allows us to construct the result.
Yes, and currently the latest version of Grackle is 0.8.1, so we still don't have 1.0 version, but there is plan to make it soon. Well, still, it's a GraphQL server that was already battle tested on some highly visible and high traffic sites, the ones that we mentioned in the beginning of the presentation. So I guess it's something that you may consider using. Still, there is lots of scope for contributions. So if you want to check out the project, join, make any contribution, then you are welcome. And here is the link to the project on the GitHub. Also, the list of all contributors. As you can see, the main authors of Grackle are Sabin, who you already know, and also Rob Norris, who is author of Dubi and Skank. So that's why we have these integrations in Grackle in the first place.
And just also like to add, a lot of the work that's gone into Grackle recently has been sponsored by ITV. ITV are hiring. If you are interested in this kind of work, or would like to hear more about what kind of things they're up to, please do head over to the ITV booth.
Yes, and that's basically all what we have now. If you have any questions, then we are happy to take them.
Thank you both for that presentation. We do have several questions, and I think we should have time to get to them, so let's jump right in. First off, is it possible for Grackle to solve the n+1 problem?
Yes, and it does. So all of the queries that you saw, or the data, so I think Rafał gave sort of an interesting example of a query against the database-backed model. It had several top-level queries. It had nested queries. Those will have been compiled to a single SQL statement. And you would just a single query is made to satisfy the entire query. A lot of work has gone into addressing that. That's with respect to queries against a SQL store. There is another more, if you like, more general n+1 problem. So, for example, if you could imagine a situation where you have a composition of, say, a query against a database, and then at the leaves of that query, you might suppose, for example, you were you had a query. I don't know. Well, what's the one everyone uses? Exchange rates or something like that. You might have some values at the leaves of a query, and you might want to convert those values using some exchange rate, using some external sort of a currency conversion service, for example. Although this is an area which hasn't had the most amount of practical use, there is a very sophisticated infrastructure for evaluating these kinds of queries in stages. So, for example, in that instance, we would evaluate a SQL query up to the points at which we have calls out to external services. These things would be batched together and could be executed as a, if you like, as a batch of requests against, or a single aggregated request against a remote service, and then the results of those executions could be integrated back into the rest of the result tree that we had from the database. So yes, it directly addresses the N+1 problem.
Wonderful. All right, our next question. Can you constrain the query space to ensure performance and scale for the API? In other words, aren't you afraid to lose control with such exposed flexibility?
Well, I mean, I think that's a general problem with GraphQL just across the board. Grackle provides various kinds of sort of complexity-related limits, and you can restrict width and depth of queries. But I mean, that's a fairly blunt instrument, and given bad luck and a schema which is designed in a way which supports queries which can expand in unpredictable ways in the size of their results. Yes, this is certainly a problem. I think that the mechanisms that Grackle provides, I suppose, in the sense of primitives, are helpful in this respect. Bear in mind that the things which are executed are values. So we have a term in a query algebra. It is really very straightforward to traverse these values to compute metrics over these things. Exactly what in any given instance counts as an expensive query is going to be very much application specific, but we have the tools for, on a case-by-case application specific kind of way, actually implementing those kinds of constraints.
Great. Our next question. How do you use Grackle for data filtering and sorting on ITV or a Gemini? Can you load Hero and filter, sort by friends, appears in field?
Well, kind of yes and no. Bear in mind there are no default semantics for any GraphQL. So if you want to be able to filter in a particular way, the application has to have some kind of support for that. Grackle does provide really all the primitives you would need to be able to implement that kind of filtering, but it doesn't mandate. So, for example, if you have a field which returns a list of some kind of values, it does not have by default a mechanism which I mean, there is no as it were out of the box interpretation for say a filter or an ordering or what have you. However, the application developer is in a position to, using that elaboration of field arguments to construct exactly the kinds of filtering and sorting that they want for their application, and that's specified in terms of translating those field arguments into combinations of filter, order by, and limit, and offset, and what have you. So the answer is, could you filter and sort by friends and peers in fields? The answer is yes, but there is work that you would need to do to actually specify that a filter and sort on appears in specified as an argument on that, or specified as an argument of the hero field, that you would have to define the mapping between the arguments of that and the operations in the query algebra that you would need to give you the result that you wanted. But yes, you can do it.
Yeah,
Great.
and as far as I know, we have some examples. I mean, usage of this kind of things in ITV. I mean, filtering. There is some kind of filtering in our API.
I read this as very specifically relating to that particular example with an appears and field. Yeah, I mean, absolutely. I mean, we use filtering, sorting, filtering extensively in all of the applications that we showed screenshots of earlier on. But each of those examples, we need to define what the meaning of a particular sort or filter is.
Yes.
It's not something that happens just by magic. Is I guess what I was trying to say.
All right, moving on to our next question. What is the difference between Sangria fetchers and Grackle approach for solving N+1 problems?
Well, I mean, Sangria. I mean, I'm not quite sure how best to explain this. So, I mean, let's talk specifically about say the SQL version of this problem. So in this instance, we are there just isn't an N+1 problem at all. I mean, the N+1 problem is an artifact of a sort of a particular kind of asynchronous approach to resolving queries. If the way that you resolve queries is by, say, performing some kind of operation which, if you like, resolves a sort of a root node, which then gives you a number of sort of continuations, which you then execute sort of dynamically following that, then yes, you have a problem whereby you have a sort of an expanding frontier of as yet unresolved queries. And if each of those unresolved queries requires some interaction with an external service, if each of those sort of leaves, if we imagine expanding those things out, requires an independent query against an external data source, then obviously you potentially have an issue of generating large numbers of queries against an external data source. Grackle doesn't do that at all. It will take your query and turn it into a single database query. So there is no N+1 problem. There is just a one query solution.
All right. And let's do one more question. Do you mean we no longer need to write SQL queries with Grackle?
Yes.
Wonderful. All right. Well,
I'll just qualify that a tiny bit. I mean, it doesn't mean that it doesn't mean that you don't have to care at all about the structure of your database. I mean, quite the opposite, actually. I mean, what Grackle allows you to do is focus on your GraphQL schema, your database schema. This is you need to understand how your database works, and then you need to specify a mapping between the two. Given those things, then no, you don't need to write SQL queries. Grackle will work out the SQL query that you need to make. Given the GraphQL schema, given your query, given your database schema, it will work that out for you.
Yeah, unfortunately, it does not work for mutations. So for mutations, you need to have the SQL queries. But for all the queries, yes, that's correct.
Yeah, that is absolutely right. I mean, the reason there is, again, there are no semantics for mutations in the GraphQL specification. I mean, at least with queries in the GraphQL specification, we have this kind of nested sort of data model, which is sort of implicit in the way that the GraphQL schema itself is defined. Mutations, they don't really say anything. You literally have a collection of field arguments, and then the promise that the server makes is, you send me this query, or this mutation rather, with these field arguments, I will do something, and then I will perform a query on the result of you having of that having been done. If what your mutation does is it mutates the database, then absolutely yes, you would need to write SQL to do that part of it. But the query part, the part that returns results, having modified the database, that SQL is compiled by Grackle.
Wonderful. All right, let's go and actually squeeze in one more question. I think we've got time, and there's so many questions. But does Grackle allow field level authorization? For example, restricting access for particular fields in the graph?
No built-in support for that, but you could build it.
All right. Well, wonderful. Let's go ahead and wrap it up there. Thank you so much for taking the time to answer so many questions. Thank you for the wonderful presentation. Thank you both for being here. And I hope you enjoy the rest of ScalaCon.
Thanks.
Thank you.
Fire in retro rock.
Roger, Matt. Ready to eject.